So, dear students, I welcome you for this lecture series of chemical equipment design. Today, we are going to discuss the agitator shaft design. Now, when we talked about the agitator, the one important thing is that a shaft and the connected impeller. We have already discussed the different types of the impellers. Now we will focus on the shaft, its designing, its different stresses, then what are the reasons of failure of the shaft, what must be the shaft material, in general, what is the strength of a shaft, and what treatments are given for the shaft that we are going to discuss today. Now, what a shaft is nothing but a cylindrical section and is used for rotating an agitator or an impeller in the mixing vessel. Not only in the mixing vessel, this shaft that is coming into the picture, it is also used in case of your pumps. The pumps are also more or less similar to this, that is a motor which is connected to a gearbox and then that is connected to a shaft and then it is to a pump. Now instead of pump, our case of agitator, it is connected to the impeller. So shaft can fail due to the different reasons. First thing is that the fatigue which may result due to the presence of cyclic overload. That means a continuous cyclic overload is there. As it is continuously rotating, the shaft that is rotating, so it is having a continuous cyclic load which is associated with that. That is one of the reasons for failure. Then next is a stress concentration or the wrong adjustment of bearing. That means the bearing is not properly adjusted. Shaft and the bearing, they should be properly adjusted. If it is not the case, then the stress concentration, that means the stresses are concentrated at one particular point in the shaft and from there the shaft can break. Or the insufficient clearance, that is the bearing and the shaft, there should be a certain clearance. The shaft should not be cut or get damaged. So these are the probable reasons of the shaft failure. Now to avoid these reasons, what must be the properties of this shaft? That is, this shaft should be of sufficient strength. One important thing, it should have the higher strength. And in general case, the mechanical strength is ultimate tensile strength is around 8,000 kgs per centimeter square, that is of the carbon steel. And second is the elastic limit, that is also important consideration in designing of the shaft. One is the ultimate tensile strength which is having the value of 8,000 kgs per centimeter square, and the second the elastic limit that is having the value of 5,500 kgs per centimeter square. Then next is the desired property, that low sensitivity to the stress concentration. Third, ability to withstand the heat, temperature and wear resistance. Not only that, the corrosion resistance should also be there. So ability to withstand the heat, that is temperature, wear resistance and the corrosion resistance. Then it should be good machinable. Machinability characteristics should be associated with the selected metal. Now next is it is made from which different materials. Generally it is the carbon steel or stainless steel that is preferred as the material of construction. For carbon steel, the ultimate tensile strength is 8,000 kgs per centimeter square and the elastic limit is 5500 kgs per centimeter square. Now, the strength of this carbon steel or stainless steel, that is increased by heat treatment. So certain heat treatment, nitriding atmosphere, that is made certain hard to increase its strength. So shaft can be manufactured by either hot rolling, cold drawing, or turning, or grinding from through the bars. So that is main concern. What are the probable reasons of failure? What are the desired properties? Then from where it is made, which material of construction, and how it is manufactured. This is all related to the shaft. So shaft can be manufactured by either hot rolling, cold drawing, or turning, or grinding from through bars. Up to 75 to 90 diameter, hot rolled or cold drawn shafts are used, while above that diameter, the shafts are machined from hot rolled carbon steel. Now, during the operation, shaft is subjected to pure torsional loading and pure bending load. Now, what are the different stresses that can be acting on the shaft? We can see our fan, which is hanging from a U, which is that U is there in the slab, and to that slab, to that U, the shaft is hanging. So it is the case that shaft is hanging or with the help of the hand. I am holding it with the help of a hand. So this shaft that is hanging. Now I am moving this shaft, right? So it is having a certain perpendicular motion. Now this is going to develop the bending moment. So bending moment, that is one thing which is acting on the shaft. The second, while rotating the shaft, the torsion that will be created, the twisting movement or the torsion that will be created, I am going to twist it. I am going to twist it so that the torsion that will be created on the shaft, vertical overhang shaft. So these two are the main considerations for the shaft designing. That is, one is because of the pure torsional loading, and second is because of the bending load. And the third situation is that at the same time the torsion and bending load both are acting. But this bending moment will act only when there is the abnormality in the blades. That is, if the blades get damaged, or the blades get jammed, or some blade is not properly aligned. That means instead of its this position, one has kept it like this. Then also the deformity in the movement that will take place, and your shaft moves like this. Shaft is not steadily moved, continuously moved. It takes certain rotation, and accordingly that the bending moment will be developed. So torsion as well as the bending moment, that can be in situation when the unbalanced situation is observed into the blades. So unbalanced force resulting from such situation act at a distance of 3/4 of the radius from the center for the full length blades. Now, the bending moment and shear stress, how they are calculated. The bending moment that is calculated as M, which is equal to 2886 into PS into the H upon N, where M is the bending moment and having the units of Newton meter. PS is the power. In that we are incorporating the efficiency of gearbox also. H, the shaft overhang, the length of the shaft which is overhang. At the top it is holding. So it is what? The overhang length. And N is the impeller speed at which the impeller that is rotating. This is in the RPM. Now second situation is that of a torsion torque, or now this is a chalk. You must have cut this chalk into the two pieces by applying a force in this fashion, right? You will get the two pieces. Now to this same chalk I am going to apply a twisting force, a torque, that is I am going to apply it. Now I am going to twist it, twist this chalk. How it will cut, that you have to observe it. So I am going to give a twist to this. So you can see that the chalk that is cut like this. It is cut into the two pieces, but you can see the surface area twisting has been observed. Now if I will simply cut this chalk into the two pieces by applying this force, it will cut into such pieces, right? There is a difference between the application of a force. So how I am going to apply a force? The chalk will get damaged in that fashion only. So when I have applied the force like this, it is cut into two pieces. When I have applied the twisting force, it cut into this situation. So this is the result of application of a force, application of a stress. So such different situations that can be observed. That means when the shaft is getting damaged with such situation, that means it is damaged because of the torque or damaged because of the twisting. Now you can also imagine that your hand is getting twisted, right? You can twist your hand. So there is a certain force, twisting force, we can experience in this section. When we twist our hand, you feel this twisting stress. Now I am applying this force like this. I can feel the tensile stress. This is what is a twisting stress. I am going to apply the force in this fashion or force in this fashion. So you can also imagine and understand the different forces when applied to your body. So shear stress due to torque, that is calculated as T, which is equal to 9564 into the PS upon N, where torque is having the unit of Newton meter. M is in the RPM, P is in the power. Now next situation is the shear stress calculation. So first we have to consider the load, we have to consider the bending moment or torque, and then we have to calculate the stresses. The stresses, which is equal to torque upon Z, that is the sectional modulus. So shear stresses, that is equal to the m square plus t square whole raised to 0.5 upon pi ds cube upon 16. Pi ds cube upon 16 is nothing but the sectional modulus, and m square plus t square whole raised to 0.5, that is what the average. Now this is what is a combined torsion and bending load. So in this formula we are calculating the stresses because of the combination of the bending moment and the torque. Both are taken into account. Bending moment as well as the torque that has been taken into account. So the average of that upon this sectional modulus, which is pi ds cube upon 16. So this is related to the shear stresses. Now bearing load that can be calculated as the BL into dB. BL is the bearing load and dB is the bearing span, and this is nothing but equal to the bending moment. So from this formula you can calculate the bearing load, but the bending moment, whatever the value that is there, this service factor of 4 to 5, factor of safety that is to be incorporated. Now everywhere we are incorporating the factor of safety, lambda, and while designing the shaft, generally 4 to 6, that is the factor of safety, is taken into account. So the bearing load into the bearing span, that will become equal to 5 times the bending moment. Fs is the shear stress of the material. Now this is related to the combined bending moment and the torsion. Now there are different situations which arise due to the operation, that is the load at steady state and load which is fluctuating. So what is mean by load at a steady state and what is mean by a fluctuating load? We all start our fan. Now if the fan speed which is kept at a 5 and it is started suddenly, what you will call it? It's a sudden jerk that has been provided. A sudden jerk that has been provided to the shaft. So immediately it will increase its speed. But from 0, it will have a sudden jerk. So this is what a fluctuating load. Now the fan is rotating at a constant speed of say 3. So there is a continuous load that is exerted. This is load at a steady state. So load at a steady state and the fluctuating load, there is a difference. Fluctuating load, when we give a sudden jerk from 0 to 5, that is a sudden jerk. If I will increase the speed from 2 to 3, then it will be considered as minor jerk or the minor shock or light shock. And when it is constant at a speed of 2 or constant at a speed of 3, it is considered as a steady load. So steady load, light shock and heavy shock. These are the 3 different situations that is there. Then there is a solid shaft and a hollow shaft. Now whatever the fan we have put, is it a hollow or is it a solid shaft? It is a pipe, so it's a hollow shaft. But in industries you can get a solid shaft. So you have to calculate the stresses in the solid shaft as well as the stresses in the hollow shaft. So both the stresses we can consider. Now one by one we'll talk related to the 2 situations, that is one is the pure torsional load and second is the pure bending moment. Now first, when the shaft is subjected to the pure torsional loading, the maximum shear stresses induced in the shaft. So only we are considering the torsional load, torque, T. So this will be Fs, which is equal to T upon pi d cube upon 16. So T is the torsional moment, which is having the unit of kg centimeter. D is the shaft diameter. Now, the case of a hollow shaft. So Fs, which is equal to T upon pi do raised to 4 minus di raised to 4 upon do into 16. So this is the situation to calculate the shear stresses in a hollow shaft with pure torsional loading. Only pure torsional load that has been taken into account. So by simply substituting or taking out the DO out of the bracket, so DO will get cancelled and DO raised to 3 that will be there. So DI upon DO, which is nothing but the K. DI upon DO, which is nothing but the K. K is the ratio of inside to the outside diameter. Now the other way to calculate the torque, that we have already considered the formula 9564 PS upon N, which is having the units of Newton meter. Now there is also the another formula, torque to be transmitted by the shaft can be calculated as in terms of a horsepower. So HP into 4500 upon 2 pi N. This is the units of kg meter and N is in the RPS. So from here you can get the value of torque by considering the power and the speed of rotation. Now, what will be the actual value depending on the applied load? This is what a theoretical torque I have calculated. But what will be the actual torque when the different shocks that has been provided? So Ks is the factor which is taken into account, and the design value of the torque that will be equal to the Ks into the T. Design value of the torque T will be equal to the Ks, that is what is the factor depending on the load applied and the torque. For generally applied load or steady load, Ks value is 1. For suddenly applied load or the light shock, that means for gradually applied load or steady load, Ks which is equal to 1. That means the speed is at a constant. Or we are having the different regulators which is gradually we can increase the speed. So such loads they can be also taken into consideration. And the second situation is for suddenly applied load, light shock. That means speed is increased from 2 to 3 or from 3 to 4. That is Ks is taken as the value of 1 to 1.5. And for suddenly applied load, heavy shocks, that is speed is increased from 0 to 5 directly. So this is the suddenly applied load. So design value of torque which is equal to Ks into T. So the shaft diameter that can be calculated as the Fs, that is nothing but the stresses into pi d cube upon 16, which is equal to Ks into T. Here we have considered the load, suddenly applied load. So this is for the solid shaft. Now in case of a hollow shaft, I have to apply or multiply it by 1 minus k raised to 4 for a hollow shaft, as we have already derived it here. The difference between the two equations is that this is for the solid shaft. This equation Fs, which is equal to 16t upon pi d cube, is for the solid shaft, and stresses Fs, which is equal to 16t upon pi d cube into bracket 1 minus k raised to 4, is for the hollow shaft. That means 1 minus k raised to 4 that has been incorporated for a hollow shaft. The same thing here also, 1 minus k raised to 4 that has been incorporated for the hollow shaft. Now the design stresses of material for the shaft. Generally, we are having the value of tensile strength, ultimate tensile strength. What is that? Ultimate tensile strength. I am going to apply the tensile force on this solid shaft. This value I can get it. So design stress of material for the shaft, which is taken as the Fs, which is equal to 0.3 into the tensile stress at elastic limit, or the Fs, which is equal to 1.8 into ultimate tensile stress. Ultimate tensile stress for the carbon steel is taken as 8000, which we have talked about, and for elastic limit we have considered it as the 5.5600 kgs per centimeter square. So for commercial steel, it comes as the value of Fs is around 560 kgs per centimeter square. So since the key way has to be provided in the shaft, key way, that we will talk in the next class. Now the above situation is that of pure torque or the torsional. Now the second situation is that of a pure bending load that is to be taken into account. If the shaft is subjected to a pure bending load, this is the second situation. What will be the stresses? Ft is nothing but the tensile stresses that will be taken into the account. That is, the tensile load is affected because of the bending moment. The shaft is overhang. So the tensile stresses that will be developed because of its weight or because of its further movement. So tensile stresses. And when it is a twisting, it's a torque that will be developed. So this is the bending load that is taken into account. Maximum stresses, maximum tensile stresses Ft, which is equal to m upon pi d cube upon 32. So which is equal to 32 m upon pi d cube. This is for the solid shaft. Similarly, I can write it for the hollow shaft, incorporating 1 minus k raised to 4. So this is for the solid shaft and for the hollow shaft. These are the considerations for the bending moment. Again, for the bending moment, there is some correction factor that is to be taken into account depending on the quality of a load. So for gradually applied load or steady load, Kb values, this is the bending moment values, that is equal to 1.1, and for suddenly applied load with the minor shock, Kb, which is equal to 1.5 to 2, and for suddenly applied load, heavy shock, that is Kb, which is equal to 2 to 3. This is the design values of the bending moment that will be equals to the Kb into m. Similarly, what we have done in case of a torque, there is a Ks, constant Ks that is incorporated. Here for bending moment, the constant Kb that is incorporated. Now, what will be the resultant stresses? So, resultant stresses, they are calculated by using the two different theories. One, if the shaft is subjected to the combined torsion and bending load, then in such case the maximum shear stress theory talks of Fs max, which is equal to 1 upon 2 root of Ft square plus 4 times Fs square. Ft is the tensile stresses, Fs is the shear stresses. When we twist, it becomes your shear stresses. Shearing हो रहा है like this. Layers के ऊपर layers cross हो रहे, यहाँ पे भी layers के ऊपर layers cross हो रहे, and that is why you get such damage that can be observed when the twisting that is provided. So this is the Fs, shear stresses. Shear stresses कब आते हैं? जब मैं उसको ट्विस्ट कर रहा हूं सॉलिड शाफ्ट को. When it's a cube, then the layer by layer a rhombus that will be created when I apply a shear stress. That is, for example, for this book, I am going to apply the shear stress in this way. So book that will be observed such curve, right? You can see a certain angle that is applied formed when the shear stress that has been put in this direction. Now original book is like this. I am applying a shear stress here so that book changes its dimension, right? So this is what the application of a shear stress to a square or a rectangular block, and application of shear stress to the cylinder, it creates a torque. Twisting हो रहा है उसका. So the maximum shear stress, which is equal to the 1 upon 2 Ft square plus 4 times Fs square, and second is the maximum principal stress theory, which is Ft. Ft is the tensile stresses. In maximum principal stress theory, Ft that is taken into account. In maximum shear stress theory, Fs that has been taken into account. That is, this is the maximum shear stress theory. So, failure that is occurring because of the shear stress, maximum shear stress that has been occurred. And second situation is that of maximum principal stresses. Principal stresses is the tensile stress. So, when the failure that is taking place because of the maximum tensile stress. So, these are the different theories by which the failure that can take place. So, we are taking into the account this maximum shear stress theory, which is incorporating the Fs max, and maximum principal stress theory, which is incorporating the Ft max. दो अलग-अलग theories है. Because we are taking that because of the maximum tensile force, the failure takes place in the maximum principal stress theory, and the failure takes place because of the maximum applied shear force, that is called the maximum shear stress theory. So depending on this, we are having the different formulas to estimate the maximum shear stress and the maximum principal stresses induced in the shaft. Okay. Now we have already calculated the values of this Ft and Fs. So we can substitute this value of Ft, Fs as 16K. From here I can substitute the value of T as value of Fs, that is equal to Ks into T into 16 upon pi d cube. In this equation, Fs I can substitute here. And similarly Ft I can substitute as 32 m upon pi d cube, right? Here I can substitute Ft as 32 m upon pi d cube. So after simplification of this, after simplification by substituting Ft values and Fs value from the above equations, I will get this situation. So 16 pi do cube, that can be taken out as the common, and root of kb into m square plus ks into t square, that will be there. 1 upon 1 minus k raised to 4, this will appear when the hollow shaft formulas they have taken into account. So I have to take into account the formulas related to the hollow shaft, which is incorporating 1 upon 1 minus k raised to 4 in the Ft, and also in the Fs 1 minus k raised to 4 that has been taken into account. Then this situation will appear. This is because of the maximum shear stress theory. Now similarly, in case of maximum principal stress theory, I can substitute the values of Ft and Fs, simplify that, so that I will be getting this formula. Again, this is written for the hollow shaft. You have to write it for both the solid shaft as well as for hollow shaft. So design stresses Fs, which is equal to the 0.3 into the elastic limit in tension, Fs which is considered as the 0.18 into ultimate tensile strength. वरती जे आहे that is 18% पाहिजे तिथे, or that will become 0.18. Here it is 1.8 written, instead of that it is 0.18 what is required. So it is 0.18 into ultimate tensile strength, Ft which is nothing but 0.6 into the elastic limit in tension, 0.36 into ultimate tensile strength. So for commercial or general use, Fs, that is the maximum shear stress values, are taken as 560 kgs per centimeter square, and maximum tensile stress value are considered as 1120 kgs per centimeter square. If the shaft is provided with the key, then the shaft value that will be taken as 0.75%. Now for this is called the term kb into m square plus ks into t square. This is called the twisting moment, and the second term, that this is called the bending moment term. Now these are coming from our formula. This is what the kb m square plus ks into t square, that is nothing but because of the twisting moment. Because of the twisting moment. Twisting moment क्यों आ रहा है? Is the torque. ट्विस्ट कर रहा हूं मैं तो टॉर्क अप्लाई कर रहा हूं. टॉर्क अप्लाई कर रहा हूं तो कौन सी स्ट्रेस आ रहा है? shear stress आ रहा है. And so this maximum principal shear stress theory, that is related to the twisting, application of a shear. twist कर रहा हूं मैं, टॉर्क अप्लाई कर रहा हूं. So from there it is called as the maximum shear stress theory. It provides you the twisting moment. And maximum tensile stress theory, that is providing you the equivalent bending moment. So equivalent bending moment is calculated by using this formula, and equivalent twisting moment is calculated by using this formula. Now we will talk or discuss one problem associated with this. So one by one we'll consider the example. So calculate the diameter of a shaft used in agitation system. Torque acting over the shaft is 115 into 10 to the power 3 kg centimeter, while the bending moment acting over the shaft is 34,600 kg centimeter. The ultimate tensile strength of the shaft is taken as 6,900 kg per centimeter square. However, the ultimate shear stress is 75% of the ultimate tensile strength and the factor of safety used is 6. So what is all the calculations are based on your ultimate tensile strength of a shaft material. Ultimate tensile strength, ये जो कुछ अप्लाई कर रहा हूं मैं टेंसाइल फोर्स, उसका जो है वो अकाउंट हो रहा है, दैट इज अल्टीमेट टेंसाइल स्ट्रेंथ. दिस इज द मैक्सिमम. उसके प्रोपोर्शनेट में अदर स्ट्रेसेस they are taken into account or they are getting reduced. So ultimate shear stress, this is, I am going to twist it, shearing is the 75% of the ultimate tensile strength. But however, for factor of safety, that is taken as 4 to 6. So in this numerical, we are going to take the factor of safety as 6. So permissible tensile stress Ft, permissible value, this is taken as the ultimate value upon the factor of safety. And similarly, the permissible shear stress, which is 0.75 times the ultimate tensile strength upon the factor of safety, that is taken into account. And in this case, we are assuming the load to be steady. So Ks and Kb values are equal to 1. So our equivalent twisting moment formula, which is equal to Kb into m square plus Ks into t square, reduces to root of m square plus t square. So substituting the value of m and substituting the value of t, and then equating this as the equivalent twisting moment. So I am going to consider the Fs value, right? Fs into pi d cube upon 16, which is equal to this equivalent twisting moment. So diameter comes as 8.93 centimeter, and similarly, by using the equivalent bending moment, that is from the maximum principal stress theory, which talks related to the maximum tensile strength, there you get the equivalent bending moment. So equivalent bending moment, which is equal to 1 upon 2 into bracket m plus root of m square plus t square, substituting the value of m upon t, m and t, you will get this value for the equivalent bending moment. Now this is the equivalent bending moment. This corresponds to the maximum principal stress theory. Maximum principal stress theory that corresponds to the tensile strength. So the bending moment formula incorporating the maximum tensile. So here Ft that is coming into the picture. Ft, which is pi d cube upon 32, which is equal to the equivalent bending moment. So by